So now we will talk about functions. And understanding functions is one of the keys to understanding lists. So named functions we define with the operator defun. It stands for definition of a function. So a named function is a symbol with a function object stored in its function slot. So that's what defun does. It takes the function and stores it in the function slot. So after we do a defun of the symbol add3, if we then evaluate symbol function for that symbol, it will return the interpreted function. Now there's a special notation, pound quote, which returns the function object rather than the literal symbol. Now don't mind these quotation marks here. Those are just there so that this will display properly. And this slide really should not have these quotation marks around this expression. This expression is meant to be bare. So let's go ahead and define this function in our buffer. I'll just use Control X, Control E. So now we have an interpreted function. So if I ask for symbol function of the symbol add3, we see it is an interpreted function, add3. That's the actual function object. In Slime, if I go inside the definition of this function anywhere and use Control C, that actually compiled the function. Compiles it on the fly. We got a little warning because the operator was already defined. But now if I ask the symbol function, it just tells me it's a function. It's compiled rather than interpreted. Let me remove these first two expressions and put them down below. I'm going to comment the rest of this buffer because I want to compile this entire buffer. So now in Slime, I'm going to do Control C, Control K. Ask me if I want to save the file first. Yes, I will. So I'll type Y. And now it compiled the entire file. So again, Control C, Control K compiles the whole file. Compiling the file also loads the compiled code. Another way to compile a file without using Slime is at the command line. We can load the result of compile file and then give the path name. As an easy way of getting the path name to this file, I'll use Control X, Control F. That gives me the path name leading up to the file. So then Control A, Control K to cut that. Control X, O to move to other window, and then Control Y to paste. We want to put this in a string, and we'll say genworks temp and then g101.lisp. That's our file name. And I'm going to do compile file on that and then load on the result of that. So that's another way at the command line. For example, if you're not using Emacs for your main editor, you can still do these kind of commands at the REPL. Compile file, load, because the compile file itself returns a FASL. .FASL is a compiled file. That's a binary, and it will be platform specific. So the FASL file is different depending on what type of operating system you're on, what type of Lisp you're running. The source code, of course, ideally will be the same no matter where you go. So again, load of the compile file of that, and that's what we get. A shorthand for symbol function is pound with a single quote. So if I ask pound for single quote on add3, it's the same thing as saying symbol function on the symbol add3. It's the same thing as the operator function on the raw unquoted symbol add3. The operator function takes a bare symbol. It doesn't evaluate the symbol as a variable. So function add3, symbol function of the symbol add3, and pound quote add3 all do the same thing. They all return the same thing. And what does this function do? It takes a num as an argument and it returns that number plus 3. Pretty straightforward. Now it's common to pass a function as an argument to another function. And we've seen this before with mapcar. We'll look at mapcar again. Mapcar is a common way to map a function across a list. And again, ignore these quotes. If we were to enter this expression, it's without the quotes. So we see we're applying the function add3 to each element of this list. And more commonly, you'll see this with the shorthand of pound quote with the named function and then across a list. And this is not modifying the list. It's simply returning a new list. Mapcar is non-destructive. Now here's another example of passing a function. The sort function takes another function as one of its arguments. So we're sorting a list, we're generating a new list with list, because remember, sort is destructive. So you don't want to send sort anything that you care about preserving. But the list operator always generates a new list anyway. So sort will return the result of sorting this new list according to this function. Let's see how that works. And in descending order, similarly. Now if you see what happens elements to mylist, if we sort that parameter mylist, the return value is just fine. The return value is what you would expect. But because sort is destructive, if we evaluate mylist now, it's been modified and in unpredictable ways. So once you call sort on something, you cannot depend on that value being preserved. But if we do def parameter mylist back to its original value, and now when we call sort, if we set q mylist to the result of sorting mylist, now mylist will be okay, and it will be that new sorted value. Anonymous functions can be useful. They're defined using a lambda. So anywhere where you could have a named function, you can substitute a lambda expression. So here we have our familiar add3 mapped across this short list. If we don't have a definition for add3 already, we can make one on the fly. So instead of defun add3, you substitute the word lambda. But the rest of this is the same as the body of the defun for add3. So in this case, we're map carring this anonymous function. The definition is right there across this list. We can use anonymous with sort as well. And here we're generating a new list at every level because we want to use sort with it. Let's go ahead and def parameter this so that we can see a bit more clearly what's going on. So now we have this list of names. It's unsorted by any criteria. So let's try sorting it. So we'll say set q names, because I want to capture the result to the return value of sorting the names. So we're going to use an anonymous function. It takes 2 arguments, and each one is a pair, because each element of this list is a pair. And we're simply going to compare numerically the first of the pair 1 with the first of the pair 2. So we want to sort this based on the numbers. Sort names, and then right here we'll put in a lambda. We'll just say p1, p2, less than first p1, first p2. So now we see we're ordered according to these numbers. Now let's say we want to order according to the names. The names are the second of each one. So second of p1, second of p2, but now we want to use string less p. That's an operator to compare 2 strings. And similarly, we can have string greater p to sort in descent by name. String less than with the symbol is similar to string less p, but this one is case sensitive. String less p is case insensitive. When we define a function, we can have optional arguments, and that uses the indicator and optional. Keyword arguments are named arguments, and that uses the indicator and key. And rest is when we want to allow any number of arguments at the end. So here's an example with greeting with an optional username. So that we have this key and optional, and then it takes any number of these pairs where this is the argument and this is the default value. So let's go ahead and define this at the command line. So now if we call greeting with no arguments at all, we get hello there Jake. If we call greeting with a name Bob, for example, we get hello there Bob. Now here's a similar definition, but now we're using and key instead of and optional. So here in this case we have 2 key arguments. Username, we'll put these on the same line so it's easier to see. So there's defun greeting. This is the argument list right here, where we have an and key and 2 pairs. Username defaults to Jake and greeting defaults to how are you. Then we're generating a string with format nil. A format is a way of creating a string. These tilde A's are placeholders. The first one is a placeholder for the username. The second tilde A being a placeholder for the greeting. So let's go ahead and define that. And if we just call it greeting by itself, we get a string. Hello there, Jake. How are you? If we call greeting with the greeting itself, notice we have an argument called greeting, and there's no conflict with the function name greeting. So we'll have the greeting be good day. And notice the order is independent here. You can have greeting with username Bob and greeting good day. Hello there, Bob. Good day. Because these are keyword arguments, they take a keyword to name them when you call. So the order is independent. That's one of the nice things about keyword arguments, is that they do not depend on the order that you pass them in. And notice from this point to the end, this is essentially a p-list. So it has a key, a value, a key, a value. So it's essentially a p-list spliced in after the function. Now some of the built-in functions in Lisp also take keyword arguments. One example is a test key argument for the member function. So several functions take a test argument. So with the test of string equal, this allows us to use member with strings instead of symbols. If you recall, we said member by itself only works with things which match with EQL, like symbols and integers. But now, if we use a test of string equal, member will work with strings. In this case, we have a list of strings, and we're matching one string using the test of string equal. and that works. But if we use member without any test, then it doesn't work. So that returns nil. But member of that list with a test of the function string equal, and we're good. So let's try with this remove. So we'll try removing 3 from this list of pairs, where each pair has a string and a number. So simply removing 3 does nothing. Even though 3 appears here, it's not the actual target value. However, if we specify a test function, and this will be a lambda form again, and the test function takes the item and then the individual target item that you're trying to remove it from. So item, and let's call it target. In this case, target is each of these pairs as it tries to remove. The actual test will be if the item is EQL to the second of the target, and this works. So we see the item which had 3 is now removed. Now there's an even shorter way of doing something in a case like this. In a case like this, instead of test, there's a keyword argument called key. And key is a function which gets applied to each target before doing the EQL. So in this case, we can simply give second as the key. And that means it's going to compare this 3 with the second of each of the target, and that also works. So we've seen recursion before. Here's another example. Here we're computing the factorial of a number, which is the multiplying that number times 1 less than itself, etc., down to 1. So you see the recursive definition. We say if, by definition, if n is 0, the factorial is 1. And then if n is 1, it's also 1, because 1 times itself 1 time is 1. Otherwise, we take the number and multiply it by the factorial of 1 less than itself. So we can see that this will bottom out eventually when n becomes 1, because one of these test cases will be true. So let me go ahead and put this in, and we'll go ahead and compile and load this whole buffer with Control-C, Control-K. That warning doesn't really bother us, just bringing our attention to the fact that this is a redefinition. Now, if I compile and load again, the warning goes away, because now it's being defined from the same place that it was before. Now we'll go ahead and try it, factorial of 10, let's say, and let's go ahead and put a trace on that. Well, we don't see the actual trace because the compiler has made this more efficient. The compiler has actually removed the recursion here. But if we copy-paste this, now we're redefining it as an interpreted function. Now we can see the trace. So compiling in this case actually compiled out the recursion because it found a more efficient way to do it under the hood. Let's go ahead and untrace. Now you can see that Lisp numbers can become quite large. There's no arbitrary limit on how long an integer can be. So to formulate a recursion, some basic steps to follow is if there's a certain base case, the smallest version of the problem, then we usually supply the hard-coded answer in that case. So if it's null, then we return 0. Otherwise, we add 1 to the more general case and continue to call it on itself. So here are a few exercises just to get a bit more familiar with functions. So we're going to write one called sort numbers. Now be sure to use safe sort rather than normal sort for this so that you're not accidentally doing destructive operations. And we want to program this with keyword arguments. So the keyword argument is going to be ordering. By default, it will order in ascending order. So without specifying any ordering keyword, it'll order them in ascending order. But you could also specify ordering descending, in which case you'll get them coming down this way. Using this, a user only has to use these keywords and doesn't have to know about passing functions into the sort function. So arguably a little bit more user-friendly. We also want to have up as a synonym for ascending and down as a synonym for descent. That's as a stretch goal. And then there are a few more exercises. You can read through these yourself. So input, output. The most basic functions in Lisp are read and print. And these are more or less opposites of each other. So each one takes a stream argument that's optional. So the default is at standard input or standard output. And these are global variables that are always bound to the default, typically text terminal or Emacs Lisp buffer. On Windows and Allegro, standard input and output correspond for the most part to the console window, which is a separate window that comes up. It's theoretically infinite source or destination for data, text or binary data. Normally, we don't want to change the values of standard input and standard output, for example, with a set queue. There are other ways to locally bind these, namely with a let binding, for one example, that is more safe and less of a drastic approach than actually changing the values of standard input and standard output. So by itself, if you read, it will sit there and wait for some input from standard input. So if we go in our REPL and type read, it's going to block. It's going to wait till I type some expression. Let's try the number 10. So it read the number 10 and it returned what it just read. That's why you see a return value of 10. You could catch that result by set queuing some variable. So in this case, we're simply experimenting with a variable at the top level. So I'm just going to use setQ without doing a def parameter first. I'll say setQ my var to the result of a read. And again, it's waiting for input and give 108. So now my var. Now prints an expression, and it does follow it by a new line. It also returns the item. So if we print something at the REPL, you'll see it show up twice. Once when it actually prints it, and another time which is the return value of the function called print. If we do more than one thing, then you only see the return value of the last one, as is typical. But both side effects happen. They both print it. So you can specify the destination or source to be somewhere other than the default. So we'll see how to set a stream to point to a file, an open file. And then only the printed data will go there. The return value doesn't go anywhere unless you specifically print it somewhere. So the facility for emitting characters to an output stream, that whole facility is known as the printer, the Lisp printer. And we have some common functions. Print we just saw. Printc is like print, but it doesn't put a new line afterwards. And in general, printc is more appropriate for making output for someone human to read it, while print and print1 generate output that Lisp can easily read back in. Format is a powerful generalization of all of these things that allows you to specify a string with substitutions that get printed. So format is very general. It takes a stream. The stream can be nil, in which case it just returns a string instead of actually printing anywhere. The stream could also be T, which means standard output. That's shorthand for standard output. And then the format string. So here's the format string where anything that starts with a tilde is a special directive. And the general one is tilde-a. And that just substitutes the argument as if by printc. As if you printed this with printc, that's what gets substituted into the string there. So it's just a bob. It doesn't have the extra decoration of extra double quotes around because printc doesn't print with double quotes. But if the stream is specified as nil, it comes back as a string. So the format string is a template. The directives start with a tilde. They form their own language, powerful language. You can look this up in a Lisp reference. Most commonly used directives are tilde-a and tilde-s. Tilde-a will process as if by printc. So namely, it strips double quotes off strings, it strips the colon off the beginning of a keyword. It's intended more for human output. Tilde-s prints as if by print1, and that means it's more machine-readable output. So strings will have the double quotes around. Keyword symbols will have the colon in front of them. This means that Lisp itself can read these values back exactly as they were printed. So it's good for round-tripping information out and back into a Lisp program. And here we see keyword symbol printed with tilde-a just prints without the colon. Here are some other online resources for complete treatment of the format directives. Tilde-f processes a floating point number according to many options that you can give with comma directives to determine, for example, how many places after the decimal point, etc. Now, tilde-f does not predictably round the number. If you want to round the number, do it yourself first. There's a function round. There are other similar functions we will see later before passing it to format, just to be sure that the rounding is happening the way that you expect. So to go in and out from a file, we still use streams, but the first thing is we have to connect the stream to a file, either for reading or for writing. In this example, we're actually opening a file, and by default, the file will open read only, and we're binding this open to a stream. Now we could read some values from this stream, and then if we do it this way, though, we have to remember to close the stream. You have to close the stream explicitly. So there's another macro that we use more frequently called with open file. This will automatically close the stream, whether an error happens or not, when the with open file is closed. So even if an error happens while doing this read and you come out of the error, the stream will not be left dangling. So in this case, we're letting a path name, and a path name can be given just as a string like this. And tilde in a path name, of course, is shorthand for home directory. That comes from the Unix world. That'll also work on Windows in Lisp, though. So with open file, and then we give the stream, which is a name that we make up. That's just a variable name that names the stream which will be created from this path name. And again, default is read only, and in this case it will read one value from that input stream and return it, which is hello. So with open file automatically closes the stream. If we want to do writing out to the file, then there are some extra keywords we have to give. Of course, these can be abstracted away, but in the bare form of the with open file, we do have to give direction output if we want to be able to write to the stream, and to specify what happens if the file already exists. In this case, we're saying supersede. You could also say append, or you could say error. And if does not exist, what is the action? Either create or error. And then we format our same format operator, but now we're, instead of nil or t, we give an actual stream, which is the output stream that we've established inside this with open file. And in this case, we're writing a constant string out to that stream. So we have a few exercises for this section. We'll create a file which contains a simple plist, just a plist in the file. And the keywords will be keyword symbols, the values will be any expression, and then you want to make a function in a separate file, make a function called read plist, which takes the path name as an argument, and it'll read the first valid Lisp form. So in this case, it should read the plist out of the file that you just created. Next, you'll want to read that plist into a let variable and put a prompt to the user, again using read, to let the user type a keyword symbol. And then if that value exists in the plist, return that to the user as the return value of the function. And this last exercise you can read on your own. That's a bit of an extra credit. It also assumes a bit of HTML knowledge. Now numbers. What types of numbers do we have in Lisp? Integers, which have no arbitrary limit on their size. Floating point numbers can be expressed with a typical point, decimal point, or with the exponential notation. And ratios. Ratios remain as ratios. They don't arbitrarily get divided into decimals and cut off at a certain precision. Complex numbers are also defined in Common Lisp. So if you try to take a square root of a negative number, you will get an answer, which has an imaginary part and a real part. Integers, we can use equal. But normally, it's not a great idea to use the equal symbol operator for floating point numbers, because there could be some infinitesimal difference if you're dealing with floating point numbers due to round-off error. So the GDL function near to is provided for checking if two numbers are within an epsilon to each other. Greater than operator takes any number of arguments, and it will return true if all the numbers are in the correct order. So it's the same thing as saying 3 is greater than 4 and 4 is greater than 5, if we string them all along like this. Plus P checks for positive, if it's a positive number or not. Minus P if it's minus or not. 0P checks if the number is actually 0 within a certain epsilon. Max takes any number of arguments and returns the max from it. Min takes any number of arguments and returns the min. Notice that each of these don't take a list exactly, they take a rest of arguments. So there is an operator which will apply a function to a list, making it so that this list becomes all the arguments directly to the function. Essentially, it will splice the list onto the function call. So if you want to take the max and you already have a list, then this apply is the way to do it. Apply the function max to our list, apply the function min to our list, and you get the answer. Normal arithmetic operations, plus, times, divide. But again, divide will give back a ratio if it can. That's more precise than an arbitrary decimal point, floating point number. Notice plus just by itself gives the additive identity 0. 1 plus is actually a function that just returns its argument plus 1, and 1 minus is a function. These are non-destructive. They simply return either 1 greater than or 1 less than the argument. Incf is a destructive analog to 1 plus. Incf will actually take the number and destructively increase it. Decf similarly. Now, Lisp does have hash tables. For certain situations, maintaining a hash table allows very fast retrieval of data based on keys. So in a sense, it's a faster version of a plist. For accessing values, we use getHash. And note, there are reasons for this, but just take note right now that getHash takes the key as its first argument and the hash table value as its second argument. Arrays allow you to represent indexed vector or a multi-dimensional matrix that are indexed based on integers. Now, GDL has some built-in data types called sequences, which are much like arrays. And in many cases, you can simply use the GDL sequence rather than resorting to a low-level Lisp array. Common Lisp defines def struct for a structure with slots. There's a complete object-oriented system called class. Now, in GDL and Gendel, we have the define object operator, which actually piggybacks on top of class to give objects with a bit richer behavior than just class objects. But these low-level class objects and structures continue to exist even with GDL or Gendel present. So one exercise here, it's a bit of an extra credit actually, but create a memoized version of factorial. So it'll store all the values that it's computed in a hash table. And note, this is key for this exercise. You can actually wrap a let binding around the function definition. So you can let a variable and then within that have your def on. That means that def on icon only will have access to the let variable. A little bit about symbols. In Lisp, packages are namespaces for Lisp symbols. It's like an area code for symbols. And we can use packages to avoid name collisions. So packages provide one aspect of modularity to developing a Lisp project. Non-key symbols are typically interned in a certain package. So if they're in different packages, they will not be EQL to each other. Keyword symbols are all in the keyword package. And this is the printed representation, but this is really shorthand for saying keyword colon and the symbol, just showing it with a keyword on the front. So two keyword symbols with the same name will always be EQL to each other. So in GDL or GWL, if you're doing web interfaces, you can use the macro GWL define package to define your own package and then export whatever symbol you may want other modules to be able to access conveniently from your package. So congratulations. If you've understood most of these slides, completed most of the exercises, you should have a lot more familiarity looking at Lisp programming. There are some further resources here, and next we'll start into G102, which will bring you up to speed in GDL itself.